Hello, this is RobertPierrard. Together with Javier Eladio, we investigated a study of a blast effect on a human torso. Although we had originally planned to present our findings together, this is not possible due to the special circumstances. As a result, I will be speaking alone. The objective of this simulation was to study the effectiveness of a ceramic armor plate. To do this, an explosion was detonated in front of the armor. In the image, you can see the explosion as it dissipates and impacts the armor. Experimentation is essential for testing the effectiveness of armor. However, physical experimentation can be dangerous considering it would be necessary to work with explosives. Furthermore, you cannot analyze the effects of such explosions on a human body without risking severe injury or even death. For these reasons, computer simulation is especially useful in testing the effectiveness of armor by predicting the response of both the armor itself and the harmful transfer of energy into the human body. For a demonstration of this simulation, follow this link and watch the first minute. You will see an explosion first with and then without body armor. Going into the details of the simulation itself, both tetrahedral and hexahedral meshes were used. In total, across all meshes, there were 88,000 nodes. A high time resolution of 2 microseconds was used. This was essential considering the extreme propagation speed of explosions. This model uses several different meshes representing different components such as the ceramic plate, ribs, skin, and internal organs. In reality, each of these components have vastly different properties. As such, each component in the simulation had its properties designed separately. Examples of such properties are seen in the table on the right. This experiment ran for a duration of 15 minutes on a single i7 CPU with 16 gigabytes of RAM. This timescale makes it clear that the simulation is resource heavy, but easily runs on modern-day computers. This slide shows several images of the discrete meshes used to represent the internal organs, bone structure, vest, and ceramic plate. As mentioned, each mesh is designed with its own properties. You can now see that all the meshes are tetrahedral except for the ceramic plate, which is hexahedral. For this simulation, the method used for the explosion was smooth particle hydrodynamics. It was initially developed by Lucy, Gingold, and Monaghan in 1977 to solve problems in astrophysics. Later, in 2000, Lacombe implemented the method into the LSDYNA code to resolve large mesh deformation in high-velocity impact problems, such as the one shown in this presentation. This method is used in astrophysics, ballistics, volcanology, and oceanography. All examples of fields where tracking individual particles may be more important than mesh deformation. In the image to the right, you can see such particles impacting the rib cage and the internal organs. Now, smooth particle hydrodynamics are not applicable to what we have studied in class. However, due to Lacombe's work, it is integrated into LSDYNA, a software distributed by Livermore Software Technologies. This simulation software utilizes meshes as we have discussed in class, and it is responsible for incorporating the meshes previously mentioned in this presentation into the simulation. Furthermore, the software is optimized for both shared and distributed memory Unix, Linux, and Windows platforms. Therefore, it is very portable. Its origins lie in highly nonlinear transient systems using explicit time integration, and typical applications include automotive crashes, explosions, and manufacturing. In the table to the right, you can see some of the different system configurations for running this software. Under the HPC interconnect column, you can see that InfiniBand can be used for parallel computing as is done in the Kahan cluster at UPV. This slide shows some of the examples of data that can be created from this simulation. Starting in the top left, you can see the dissipation of the internal energy, that is, the energy within the human torso. That is accompanied by the bottom left graph, which shows the total energy of the system over time. In the bottom right graph, you can see the rigid body displacement over time, meaning the displacement of the entire body as one unit. However, you can also analyze the displacement of single nodes, or collections of nodes, as is shown in the last two images. In the bottom middle graph, you can see the displacement of individual nodes, whereas in the top right graph, you can see the displacement of entire organs. Using the data gathered from simulations such as these, one can determine the effectivity of body armor against various explosions and impacts, with the eventual goal of saving lives.